Today, I'm going to talk about regime shift in streams, real-time focusing of co-evolving time sequences. I'm Yasuko Matsubara, and this is a joint work with Professor Yasushi Sakurai. As you know, there are many kinds of social and natural phenomena. We can obtain various kinds of big time series data streams, such as environmental sensor, online user activity, and financial data, or automobile sensor, and the other kind of physical sensors, and epidemics, and so on. For example, please look at this figure. This is the example of motion capture sensor data stream. And specifically, we can see that there are 4-dimensional data points, left, right, legs, and arms. And actually, this is a walking motion. And this is another example. This is an online user activity data stream. Specifically, this is taken from Google Trend data. We can see that we have 4-dimensional time series data, each of which describes Google search volume for Amazon Prime, Netflix, YouTube, and Hulu from 2004 to 2016. And the question is that, given this kind of large collection of data streams, how can we forecast future trends and future events? More specifically, this is a problem definition of this work. Given a collection of co-evolving event stream, X, and here TC is the current time tick, the goal of this work is to forecast long-term trend. More specifically, we want to predict L steps ahead future events at any point in time. Okay, I'm going to show you the modeling and forecasting power of our proposed method, namely REGIMECAST. Okay, so REGIMECAST is a real-time forecasting algorithm for data streams. And please look at this figure. This is one of the examples of our output. And specifically, the top figure is the original data stream. In this case, this is a motion capture data. And the middle one is our forecasted result. In this case, it tried to predict 100 steps ahead future events. And bottom one is a snapshot of REGIMECAST, and we call it current window. And here the black arrow shows the arrived events, and the red arrow shows the future unknown events. And please look at this video. And this is an original motion capture data. And as you can see, this data contains various kinds of motion, like walking, moving arms, moving right arm, and so on. And the goal of this work is that given this kind of data stream, we want to forecast future long-term trend at every time tick. So now I'm going to show you the demonstration video of REGIMECAST. So as you can see, the red box is our forecasting result. And our model can automatically and incrementally, adaptively recognize the current regime, the time series pattern, like walking, moving the both arms at the same time, and left arm and right arm, like this. And also it can predict 100 steps ahead future event at every time tick, continuously and adaptively. Okay, so excuse me. Okay, so next overview. So what would be the most important point of real-time forecasting? Specifically, we want the model that can satisfy 4 important properties. That is long-term, continuous, nonlinear, and adaptive. With respect to the first 2 properties, we want to forecast long-term trend rather than just short period of time. And more specifically, we would like to predict L steps ahead future event, as shown in this figure. And also, this is a data stream, so we would like to capture dynamic evolving patterns continuously. Next properties are about adaptive nonlinear modeling. The idea is that we propose using nonlinear dynamical system to describe various kinds of complicated time-evolving pattern. Next property is adaptive. So as I mentioned before, the real-time series data contains various kinds of regimes. So that's why I propose a new concept, regime shift in stream. And this is inspired by the concept that can be seen in the real-world ecological system, I mean biology. Okay, so next I would like to show you our proposed model. Our model consists of three important ideas, that is latent nonlinear dynamical system, regime shift in streams, and nested structure. Okay, I'm going to introduce the first one. And as I said before, the real data stream contains various kinds of regimes, such as walking, stretching, and so on. And the question is that, how can we effectively capture various types of time series pattern regime for each pattern, like walking and stretching? And this is our answer. Specifically, we propose using latent nonlinear dynamical systems. And this model consists of two functions, ST and VT. And here ST, this is a potential hidden activity over time. And VT is actual observable time series data. It could be anything like sensor data or online user activity, anything. And more specifically, the potential activity S can be described as a nonlinear differential equation like this, specifically linear, exponential, nonlinear parameters. And also the VT can be described as a projection of potential activity ST. So consequently, the single regime can be described as a set of 6 parameter set, SP, Q, A, U, and V. Okay, so let's move on to the next property, regime shift in streams. So please look at this time series data. And you can see that there is a walking motion from time tick 0 to 1000. And in real data, this kind of pattern suddenly changed to the different pattern. In this case, it switched from walking to the stretch motion suddenly. And the question is that, how can we find this kind of sudden changes in the stream? And our answer is regime shift in streams. So the regime shift is a very important phenomenon that can be observed in the real-world natural system. And regime shift is a sudden changes in the structure of complex systems. So for example, we can see many kind of phenomena like woodland versus grassland, coral versus macroalgae, or desert versus vegetation. So for example, the woodland system can be alternated by the grassland, or it can go back to the woodland, and so on. And this phenomena can be described as a nonlinear differential equation. And here ST is some kind of time-evolving ecosystem property. It could be anything like nutrients and soils. And based on this phenomena, we propose a new concept, regime shift in streams. The idea is that, similar to the real-world ecosystem, we create the complex systems that can generate various kinds of distinct regimes, like walking and wiping, and it can switch to the other motion alternatively and adaptively. And this is a detailed function, the equation of regime shift in streams. I'm not going to describe it in detail today, but the basic idea is that we introduce additional parameter R, regime shift dynamics, and its parameter capture the strength of each regime at each time tick. And consequently, the regime shift can be described as a set of C different regime parameters, theta plus regime shift dynamics matrix R. Okay, so last idea is nested structure. So now we would like to capture multi-scale dynamical activities. So for example, please look at this video. This is a chicken dance. Probably you are familiar with this dance, and this is a very famous dance in the US. And this dance consists of 4 basic steps, that is beaks, wings, tail feathers, and claps. And this is the original time series data stream for chicken dance. And as you can see, this data contains various kind of complicated patterns, and it looks very difficult to understand. But we can decompose it to a set of very simple motions. And that is the long-term trend and short-term trend. So for example, please look at the tail feather motion, specifically the red box, top X original data. And it looks very complicated, but it turns out it can be decomposed into very simple 2 motions, that is bending knees once and moving arms quickly. So based on this pattern, we propose using multi-level modeling structure. The idea is that instead of modeling using just a single pattern, we try to capture long-term trend at the first level, and the next level, it tried to capture shorter pattern. And it tried to create local evolving pattern for each at each level, and eventually we can get the global trend. Okay, so next I'm going to introduce our streaming algorithm. Okay, so please look at this figure. This is a snapshot of REGIMECAST, and we call it REGIME-Snap. And here, black dotted lines are the original data stream, and the colored lines are our estimated events. So the problem definition is that given the current window XC, this is our original data from TM to TC, then our first goal is to find the estimated events, the colored lines, it's from TM to TE. And also, we are interested in L steps ahead future events. And we thus report focus window VF. It's from TS to TE. And this is the overall algorithm of REGIMECAST. And the REGIMECAST reports L steps ahead future event at every time tick. And this algorithm consists of 2 sub-algorithms, that is regime reader, which try to identify the current regime dynamics. And another one is regime estimator, which try to estimate regime parameter set theta. Okay, so and this is the overall algorithm of REGIMECAST. So at first, given a data stream X, it extracts the current window XC, and then it tries to find the optimal regime that's stored in the model database. And more specifically, this is a detailed function of regime reader. And I'm not going to describe in detail, but the high-level idea is that it tried to update model parameters theta, theta 1, 2, 3 stored in the database, and also after that it tried to identify the regime shift dynamics R at time tick TC. And next step is optional. So the idea is that if we couldn't find any appropriate regime in this database, we have to create another one. So the regime estimator basically tried to estimate the new regime parameter theta and also insert it into the database. And at the next step, the algorithm tried to estimate future events. More specifically, it generates local events for each level in the nested structure. And after that, it finally reports future events. Okay, so we also provide some efficient technique to generate the future trend efficiently. And I'm not going to explain in detail today, but we call it dynamical point set DPS. The basic idea is that our algorithm is very scalable. It requires at least order CLE divided by delta. And here C is the number of resumes in the data. And L is the number of the lengths of the estimated event. And delta is a DPS interval. And the most important point is that our algorithm does not depend on the length of the data stream. So that is, our model is very scalable. Okay, next, experiments. Our experiments are designed to answer these three important questions. That is effectiveness, accuracy, and scalability. So this is the experimental result for effectiveness, and specifically this is the data from motion capture data, which contains various kind of exercise motion. And the top figure is the original data, the middle one is our forecasted result, and the bottom one is some of our snapshot. And as you can see, our model can capture various kind of resumes such as stretching and walking and so on. And this is another example. This is the also motion capture data, but it contains various kind of house cleaning motion, like walking, using a dustpan, wiping a window, and so on. And as you can see, our model successfully capture long-term trend. And this is a more difficult pattern, chicken dance motion. And as you can see, as shown in the bottom figure, our model can successfully recognize this kind of very complicated pattern, tail feather motion, and it provides us a very good forecasting result. This is another result. It is from Google Trend data. And here, the top two figures are the original data. And left one is basically online TV related keywords, Netflix, Hulu, YouTube, and Amazon Prime, and more than 10 years. And right one is a beer related keywords. And the bottom two figures are the forecasting result of REGIMECAST, and specifically it generates 3 months ahead future events. And as you can see, our model can capture this kind of pattern very effectively. And this is another example. Left figures are the social media related keywords, and the right one is the software related keywords. And this is another types of data. This is actually environmental sensor data. Left figure are the original data which describe atmospheric pressure, and the right one is the temperature data. And bottom two figures are the 3 months ahead future events. And this is another one. This is a financial related event stream. Left one is M versus dollar, and right one is a gold versus platinum. So as you can see, our model can capture various kind of time series pattern effectively and incrementally. And this is a result for accuracy. And specifically, this figure shows the forecasting result of REGIMECAST versus other competitors, ARIMA and TBATS, which is a state-of-the-art forecasting algorithm. And as you can see, our model can successfully identify and recognize the current system, current regime shift dynamics immediately. And this is the root mean square error between the original data and our forecasting result. So again, the lower is better, and as you can see, our model can forecast future trend very effectively. And this is a scalability. Specifically, the left two figures are the wall clock time versus time tick, and the right one is the average computation time for REGIMECAST and TBATS ARIMA. And as you can see, our model can forecast future trend up to 217 times faster than ARIMA and TBATS. Okay, so last one is about the discussion. So one of the most important point of this work is that our model can focus very long-term trend. And the question is that how long ahead can our model focus future events? And this is the answer. So specifically, left figure shows the L step versus root mean square error, and right figure shows the L step versus wall clock time. And as you can see, our model can forecast future pattern for every step. Okay, now I conclude our work. We propose real-time forecasting algorithm for data stream, namely REGIMECAST, and our model is effective, adaptive, scalable, and anytime. Thank you very much.
Thank you. That was a great talk. So based on your experiment, for example, for chicken dance, you have 4 different group of moving. Did you experiment your model for more than that, like for example, 20 motions? I mean, if you have any experiment that shows that how much, I mean, in that case, this model can be effective and accurate.
Okay.
Thank you.
Thank you very much. So it's about the number of regime in the data stream. So actually, in this case, here we basically have less than 10 regimes in a single data stream, but our model can handle many patterns. Okay, so let me show you this one. So basically, our model can store all of the regimes that have already observed in the data stream, and it's stored in the database. So it can generate various kind of regimes if we already observed. But and as you said, the complexity, the scalability of this algorithm depends on the number of regimes stored in the database. So it depends on the pattern contained in the data stream. So the answer is the accuracy would be the same for any kind of data stream, but perhaps the scalability would change depending on the kind of the data. And I think that this would be our next future step. Thank you very much.
Hi, nice talk. So, couple of questions.
Sure.
First question. So, in this particular, do you assume that the time series or the time sequence you have is uniformly sampled? Is the sampling uniform?
Excuse me, could you please repeat it again?
So, is the sampling uniform? So, is the duration between the timestamps equal, or are they irregularly spaced timestamps?
Sorry, I'm so sorry.
So the question I'm asking is that you have a time series here, right? You have a sequence of events, right? Mm-hmm. So the timestamps, the time at which the event is recorded, are they equally spaced?
Timestamp?
Yeah.
So is it like weekly data, monthly data,
Is it
or is it this month and 2 months later, 3 months later?
You mean the interval of each?
Yeah, the
event?
intervals. Yeah, are they equal?
Okay. Currently, we use the same interval, but basically this model is based on differential equation. So I think our model can handle that kind of data, because I mean we don't have to use exactly the same time interval, because differential equation can handle that kind of pattern. Am I answering your question?
Yeah.
Thank you very much.
Excellent. Let's thank Yasuko again.
Thank you very much.